Welcome to a world where objects float in midair without any visible support. This isn't magic or science fiction, it's acoustic levitation, a fascinating phenomenon where sound waves, completely invisible to the human eye, suspend matter against gravity. Today, we'll explore how this technology works, its surprising historical roots, and how it's revolutionizing everything from pharmaceutical development to quantum computing. Join me as we dive into the science behind this remarkable technology and discover how something as simple as sound is opening new frontiers across scientific disciplines. At its core, acoustic levitation operates on a principle that seems deceptively simple but requires precise engineering. When sound waves from opposing directions meet, they create standing waves with nodes, points of minimal pressure where objects can become trapped. These acoustic pressure fields effectively counteract gravity's pull, allowing matter to float in apparent defiance of nature's fundamental force. Most acoustic levitation systems employ ultrasonic frequencies beyond human hearing range, creating silent fields of tremendous acoustic pressure that can support objects ranging from microscopic particles to small organisms weighing several grams. The fundamental mechanism involves standing waves, patterns formed when waves traveling in opposite directions interact. When precisely calibrated ultrasonic transducers emit sound waves that reflect upon themselves, they create fixed patterns of high and low pressure in space. Small objects become trapped at the nodes of these standing waves where the pressure remains relatively constant. What makes this even more fascinating is the acoustic radiation force involved. This force arises when an object placed within the acoustic field disrupts the sound waves through scattering and absorption. The resulting pressure differential creates a force strong enough to counteract gravity. Controlling these acoustic fields with precision requires sophisticated algorithms and hardware, particularly when working with objects of irregular shapes or varying densities. Unlike other levitation methods, acoustic levitation offers remarkable versatility. As Dr. Ashir Martsu from the University of Navarra explains, what makes acoustic levitation particularly versatile is that, unlike magnetic levitation, which requires objects to have specific magnetic properties, acoustic fields can manipulate virtually any material, liquids, solids, and even small living organisms, regardless of their electromagnetic properties. This universal applicability has opened doors to applications across scientific disciplines that other levitation techniques simply cannot address. Recent technological advances have moved well beyond simple standing wave patterns. Scientists now create dynamic, programmable acoustic fields that can not only suspend objects but manipulate them with 6 degrees of freedom. These acoustic tweezers can rotate, translate, and precisely position multiple objects simultaneously. Researchers at the University of Bristol have developed what they term acoustic holography, three-dimensional pressure fields that can be reconfigured in real time for complex manipulation tasks. This level of control transforms acoustic levitation from a mere curiosity into a precision tool for scientific research and industrial applications. While videos of acoustically levitated water droplets might circulate as scientific curiosities online, the pharmaceutical industry has quietly adopted this technology for revolutionary manufacturing processes. Traditional drug crystallization methods involve container surfaces that can introduce impurities or affect crystal formation in undesirable ways. In 2019, researchers at the Karolinska Institute in Sweden demonstrated that acoustic levitation enables containerless processing, allowing pharmaceutical compounds to crystallize in midair without touching any surface. This technique produced amorphous carbamazepine, an anticonvulsant medication, with 20% higher bioavailability than conventionally manufactured versions. The practical implications are significant, potentially reducing required dosages and minimizing side effects for patients. The implications extend far beyond single medications. Dr. Bjorn Lindman, who pioneered this technique, notes, when developing new pharmaceutical compounds, Understanding crystallization pathways is critical. Acoustic levitation allows us to observe the entire process without the confounding variable of surface interactions, revealing nucleation and growth mechanisms impossible to study through conventional means. This provides pharmaceutical researchers with unprecedented insights into drug formation processes. The technique has proven particularly valuable for protein-based pharmaceuticals, where conventional crystallization methods often lead to denaturation or loss of therapeutic activity. A 2021 study published in Nature Biotechnology revealed that monoclonal antibodies crystallized via acoustic levitation retain 94% of their binding efficacy, compared to just 78% when using traditional methods. This difference translates to billions of dollars in manufacturing efficiency for this rapidly growing class of therapeutics, potentially making life-saving medications more effective and more affordable. Perhaps most surprising is the application of acoustic levitation in biological research. In 2021, a team at ETH Zurich successfully levitated living C. elegans nematodes, microscopic roundworms, for extended periods without harming them. This achievement enabled unprecedented 360-degree microscopic imaging of living organisms in their natural state without the distortions caused by contact with microscope slides. Dr. Anita Sengupta, the project's lead researcher, noted, "We can now observe cellular processes from angles previously impossible, revealing microbial behaviors that change when in contact with any surface, a fundamental shift in how we study microorganisms." This three-dimensional observation capability has transformed how researchers understand microorganism behavior. The biological applications have expanded into cell culture technology as well. Traditional cell culture requires cells to grow on artificial surfaces that can alter their behavior and gene expression. Acoustic levitation chambers developed at Stanford University now allow for three-dimensional cell cultures suspended in nutrient media without any surface contact, producing cellular structures that more accurately mimic in vivo conditions. This acoustic cell culture technique has proven particularly valuable in cancer research, where tumor spheroids grown in acoustic levitation display drug resistance profiles that more closely match clinical observations than traditional cell culture models. The implications for developing more effective cancer treatments are profound. Most recently, the technology has found applications in regenerative medicine. Researchers at Kyoto University have developed acoustic bioreactors that suspend stem cells during differentiation, eliminating the mechanical stresses that conventional bioreactors introduce. The result has been a 40% improvement in the viability of engineered tissues and a significant reduction in unwanted differentiation pathways, a crucial advancement for the production of transplantable tissues that could eventually save countless lives. The principles behind acoustic levitation have curious historical precedents that suggest this phenomenon may have been observed centuries ago, even if not fully understood. Some archaeoacoustic researchers, including Dr. Manja Sharma at the Indian Institute of Technology Delhi, have documented ancient Tibetan singing bowl arrangements that appear capable of creating rudimentary acoustic levitation effects with small objects like rice grains. These historical connections raise fascinating questions about ancient knowledge of acoustic phenomena and how traditional practices might have unknowingly utilized principles of wave physics. While modern acoustic levitation employs sophisticated electronics and precise ultrasonic transducers, these historical examples suggest that the basic principles, standing waves and pressure nodes, can be demonstrated with much simpler technology. This historical perspective reminds us that sometimes advanced scientific principles can be observed through relatively simple means, even if the theoretical understanding comes centuries later. Looking forward, acoustic levitation intersects with quantum computing in unexpected and promising ways. At the University of Southampton, physicists have developed specialized acoustic levitation chambers to suspend individual atoms for quantum computing operations. These acoustic quantum traps maintain quantum coherence 30% longer than conventional electromagnetic trapping methods by eliminating surface interactions. This improvement could potentially accelerate quantum computing development by preserving the delicate quantum states necessary for computation. The ability to manipulate individual atoms with acoustic fields provides quantum researchers with a new tool to address one of the field's greatest challenges: maintaining quantum coherence long enough to perform meaningful calculations. By eliminating the decoherence that occurs when quantum bits interact with surfaces, acoustic levitation creates a more isolated environment for quantum operations. This application demonstrates how a technology developed for one purpose can find unexpected applications in seemingly unrelated cutting-edge fields. The field of acoustic levitation continues to evolve in surprising directions, pushing the boundaries of what's possible in scientific observation and manufacturing. In 2022, researchers at Argonne National Laboratory combined acoustic levitation with specialized X-ray imaging techniques to study intermediate states of chemical reactions that occur too quickly to observe through conventional means. By suspending reactants in acoustic fields and introducing catalysts through precisely timed microjet injections, they captured the formation of transient molecular structures that had previously only been theorized. This ability to freeze-frame chemical reactions in progress provides unprecedented insights into reaction mechanisms that could lead to more efficient catalysts and chemical processes. Meanwhile, material scientists at Tokyo University have developed what they call acoustic assembly, using complex acoustic fields to position components as small as 10 micrometers with nanometer precision. This technique enables the fabrication of three-dimensional microstructures that would be impossible to create through traditional manufacturing methods. The implications for microelectronics, medical devices, and advanced materials are significant, potentially enabling new classes of devices with capabilities beyond what current manufacturing techniques can achieve. Acoustic levitation represents a perfect example of how a physical phenomenon, once considered merely a laboratory curiosity, has evolved into a transformative tool spanning disciplines from pharmacology to quantum physics. As the technology continues to mature, we can expect further cross-pollination between fields as diverse as materials science, biology, and quantum information processing. Current research is exploring how to scale acoustic levitation for larger objects, how to create more complex manipulation patterns, and how to integrate the technology into commercial applications beyond the laboratory. Some researchers are developing portable acoustic levitation devices that could bring this capability to field research or medical applications outside traditional laboratory settings. Others are exploring how acoustic fields might be used for non-contact assembly of delicate electronic components or precision delivery of therapeutic agents within the human body. The most exciting developments may come from unexpected intersections between disciplines, as researchers from different fields discover new applications for this versatile technology. What began as an interesting physical oddity has become a platform for scientific discovery with implications we're only beginning to understand. Acoustic levitation stands as a testament to how fundamental physics can lead to transformative technologies across scientific disciplines. What began as a fascinating demonstration of wave physics has evolved into a critical tool enabling breakthroughs in pharmaceutical development, biological research, quantum computing, and materials science. By creating spaces where matter can exist without contacting surfaces, acoustic levitation has opened windows into processes and behaviors previously hidden from scientific observation. The pharmaceutical advances alone, creating more bioavailable medications through containerless processing, demonstrate real-world impact that extends beyond laboratory curiosities to potentially improving patient outcomes worldwide. As we've seen, the applications continue to expand in unexpected directions, from preserving quantum coherence for next-generation computing to enabling new manufacturing techniques for microscale devices. The historical connections to ancient practices remind us that sometimes profound scientific principles can be observed through simple means, even if theoretical understanding comes centuries later. As acoustic levitation technology continues to mature and intersect with other scientific domains, it promises to remain at the forefront of innovation, proving that sometimes the most powerful forces in science are those we cannot see. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.